All right, we are live. Hello, everyone, and happy Friday. Today is May 8th, and this is episode 12 of our Google Hangouts and podcast on all things Doxis. I'm Brady Volp, founder of the Volp firm and Nimble This. With me today is John Downey, Doxis guru and consulting network engineer at Cisco Systems. John, glad to have you back with us.
Thank you. Just got back from the INTX show.
I thought it was an In Excess concert.
They're trying to regroup.
Get back together. Yeah. So we're going to be talking today about the INTX. Now I'm losing it. About the show you were at, and you'll give us an update on what was going on there. And then we have in the mailbag a bunch of questions that folks have written in. Also, if you're watching live, please submit your questions into the Q&A. Press the Q&A button up at the top of the thing. Submit your question in, and we'll also answer that. So, John, what were the highlights from the show last week? What were you guys doing, and what was going on in your booth?
So, first, happy Ocho de Mayo.
Yeah, you missed the 5th, Cinco de Mayo. I did go out and celebrate that.
I was in Chicago, but it's mainly Irish, so it wasn't so much Cinco de Mayo. It was more St. Patty's Day all the time. As many people probably know, the INTX show was previously the cable show, NCTA cable show. They rebranded it. It's kind of combined with the old SCTE emerging technologies. So there's workshops now. There is some technical papers. It's not just broadcasters with their booths. So it was interesting in that the area was shared on the north side of the hall by Microsoft's their own conference. So they had a lot of people there, and we had quite a few people there. But it's still a lot of booths, not as many people as I would normally see. But the broadcasters are all, it seems like the industry is becoming condensed, meaning one company might own 4 or 5 different broadcasters anyway, like Comcast might own quite a few. The stuff that I know that we were showing was interesting is one was the stuff that we worked out with you, the Nimble This, and the agreements we might have with your product, the Nimble This and the P&M applications. So we showed we called it cable P&M as a service. And it was offering monitoring of, and I can see this more for tier 2 MSOs. A lot of the tier 1 MSOs have their own S&MP in-house experts that can write code to do all this stuff. But to use Cisco to maybe monitor your cable plant for cable modem problems, pre-equalization information, the downstream full bandwidth capture of the modem, the CMTS, capture of upstream spectrum analysis. And as you and I talked last time about what you saw at Cable Labs Winter Conference, the upstream spectrum analysis in the modem itself, how to correlate the CMTS head-end upstream spectrum with the cable modem upstream spectrum to help narrow down where ingress could be coming from. And I have a few captures that I took while I was at the show. The big thing we were really showing, though, was DOCSIS 3.1. So it's coming along, and we're working with multi-silicon vendors. And I had a 96 megahertz wide OFDM carrier. So it wasn't the full 192 megahertz channel that you might hear quoted quite a bit for DOCSIS 3.1. It was 96 megahertz wide, 1024 QAM, 16 QAM for the physical link control channel, the PLC. The PLC is sort of like the control channel itself. So you want to make it a lower modulation scheme, more robust, and put it in a frequency is away from LTE, 4G cell phone, 700 to 800 megahertz.
So the PLC, that is really the heart of the OFDM channels. So if you lose communication with the PLC, if the modem loses that, it's going to go completely offline. That's why you're saying it has to be robust. It has to be a place that it's not going to get hit by ingress from LTE or something.
Exactly. So you can move it in the spectrum anywhere you kind of want within that channel. And you might say, well, in Chicago, Fox or NBC is transmitting digital off-air broadcast at this frequency. Well, I don't want to, ounce of prevention is worth a pound of cure. I don't want to tempt fate by putting my PLC at the same frequency where off-air ingress could come in. So I might just shift it around a little bit. So that's a couple ideas about the OFDM. And it was interesting. We were able to our cable modem guys also had a reference modem, and they did the speed testing. I wasn't doing speed testing. I was just showing on the spectrum and showing the constellation. I had a Rodian Swartz expensive test equipment to do the DMOD, so I could see the 1024 QAM constellation. And embedded in the constellation, I could see the 16 QAM PLC constellation, because it was, just, I could see the symbol landings, like kind of embedded in the 1024. But our cable modem guys are doing speed tests, and they were getting about 700 to close to 750 or so megabits per second from a 96 megahertz wide OFDM channel. If you equate that to 6 megahertz, what we call single channel QAMs, that's 16 channels of spectrum. Well, 16 channels of DOCSIS 3.0, you'll get about 580, 586, 588 if they're all primary, because there's overhead. So we're getting potentially 25, 30% more efficiency or more speed from that same amount of spectrum. But keep in mind, I'm running 1024 QAM, and I can run the 1024 QAM versus 256 QAM because of I always screw this up, the LDCP.
LDPC, low density parity check.
Parity check, yes. And then the more robust FEC and the stuff that we're doing with DOCSIS 3.1. So in a nutshell, more efficient. But because the PLC takes up space and overhead, the bigger my OFDM channel, the less that will be a percentage. You understand?
Sure. The more efficient you'll get as the wider the channel gets.
Exactly.
So now, I mean, one of the questions is, why are you limited to 1024 QAM at this time due to the hardware?
I'm just glad I can do a ping at this point.
Well, it's very very early on in the development stage of
I think we're probably 3 to 6 months ahead of where we thought we would be, and one of the holdups is going to be the silicon in the end devices, the cable modems. People are saying, should I wait for 3.1? Well, we'll have a downstream 3.1 module for our new CBR8 CMTS platform within like 3 months or so. So newer cards would be shipped with this 3.1 module. If the cards that ship today are 3.0 modules, it's an easy change out and a swap out, so that's no big deal. But I think the limiting factor would be, when can I deploy, will be based on when can I get modems. And even if I had a modem that could do downstream, are you going to buy a modem and deploy millions before you have the upstream hardware? Let's forget about software. That's easy. Well, sort of easy. Once you deploy hardware, you can't just change your mind and say, hey, let's replace millions of modems. So the modems have to have the hardware ready before people are going to buy them and deploy them. And once that happens and we deploy them, I see downstream OFDM becoming a play up front, and then the upstream will follow 6 months later or whatever. Right now we're trying to get downstream to be able to bond the 3.1 spectrum with the 3.0 spectrum, get a 2 gigabit per second pipe to offer 1 gig service. And if I offer 1 gig service, I can keep GPON from coming throughout my network. Or if I'm doing GPON and RF and HFC, maybe now with the 3.1, I can offer gigabit service ubiquitously. I don't have to cherry pick where I'm putting my GPON. You understand?
Yeah, absolutely. So, okay. So in 96 megahertz, you're seeing the efficiency, you're getting there. So it's a really good proof of concept then at the show. What was the interest in it? What were people saying?
There were some questions about, can I share the spectrum? I said on the downstream, you can't, because remember, on the downstream, your channels are always on. On the upstream, it's bursty. Channels are not always on. They only come on when the modem transmits on the upstream. So on the upstream, when we do get to DOCSIS 3.1 on the upstream, we can share the same spectrum. We can time share. So the 3.0 can burst, the 3.1 can burst, 3.0 can burst, 3.1 can burst. With the limited upstream spectrum, that's probably going to be a necessity if I need to offer higher upstream speeds greater than, say, 50 to 60 megabits per second on the upstream. If I'm limited to 5 to 42, I probably only have 4 ATMA channels. That's 108 megabits per second aggregate. I'd probably offer a 50, 55, 60 megabit per second service. If I need to offer 100 megabit per second service, I either do 8-channel upstream bonding, which forces me 5 to 65 or 5 to 85, or maybe I can do DOCSIS 3.1. And because 3.1 is almost with the OFDMA, and I can do different modulation and different spectrum and different subcarriers, I could offer up maybe some like SCDMA type of quality, it's OFDMA below 20 megahertz, where I'm not using any 18MA because I'm afraid to. And then maybe I could timeshare the 418MA, turn them off, turn on 3.1, and do the 5 to 42. That's 35 megahertz of spectrum. I do maybe 1024 QAM in some of the spectrum, 256 QAM in some of the spectrum, and 16 QAM in the real low impulse noise area. And then maybe I can get 300 megabits per second on the upstream.
And so in that lower frequency band using OFDMA, have you guys considered what type of order modulation you would be using in as far as modulation profiles and stuff like that for the OFDMA below 20 megahertz?
Yeah, that one is interesting because in theory, every subcarrier could be a different modulation. Every subcarrier, and these subcarriers are what, 50 kilohertz apart if you're doing the 4K?
But don't you have a limitation as far as CMTS processing power
Of course. That's why I said in theory. That's why I said in theory. In reality, it would be a organizational, operational nightmare. And also, how would you quantify the throughput of a channel, quote unquote channel? Because the channel now on the upstream, I think we're looking at selling a license on the upstream in 6 megahertz blocks, which kind of makes sense. On the downstream, I think we're looking at 24 megahertz blocks, even though, you might have heard quoted on the downstream 192 megahertz block, but you could sell it in blocks of 24, and then you can decide how to work that out. 24 works out well because 3 Annex A is 24 and 4 Annex B is 24. So it kind of works out real nice in that regard.
And I think in the downstream, DOCSIS standard isn't it the minimum channel size is 24 megahertz?
Yeah, you might be right on that one. So back to your question about different modulation. I think on the downstream, it's going to become sort of automated where you can look at per modem MERs on the downstream. So you have to query the modems for their downstream MER, and modems with subpar MER, you would push them into one mod profile that was kind of static, dynamic static. It's almost like an oxymoron. You're dynamically setting up or moving the modem to a statically created mod profile that's, say, robust, high speed, mediocre. So you could set up, say, 4 different mod profiles for different modems and where they are in the plant and where they are in their MER.
So you're saying robust might be all the subcarriers are at QPSK.
It could be. I mean, it could be. You hope you don't have to drop that low. Your plant's really bad, right?
Really, yeah.
But then again, I mean, there is spectrum that is really bad that you might just avoid today, but maybe we can use QPSK. Maybe we can eke out a few bits per second out of spectrum that we were afraid to use before.
Well, yeah, if we had a 10 or 20 megahertz band, well, if you do it on 6 megahertz, say we had 12 or 18 megahertz that we're using from 5 to 20, where normally we have nothing. Even if it is at QPSK or 16 QAM, that's still a lot of bandwidth that we could be using that's normally it's junk, it's noise.
Yeah. I mean, you could make the case to say, well, if it's really that noisy down there, you and I have been in this business a long time too, especially on the HFC side. If it's really noisy down there, regardless of how DOCSIS plays, what about your lasers? If you get laser clipping, all bets are off anyway. Yeah. So if it's a baseband digital reverse, maybe not so bad. Once we get to remote PHY, if we get to remote PHY and put the chipsets in the node itself, then there is no laser clipping anymore because it's a digital laser. You're doing analog digital conversion and you're just doing Ethernet back to the CMTS. So that's a little different story, and that will get us to go to the higher mod profiles for DOCSIS 3.1. I could foresee 4096 QAM on the downstream and 1024 QAM on the upstream if we do remote PHY, like remote PHY +1 or remote PHY +0, only 1 or 2 amplifiers. I think our MER readings would be good enough to support that. Sure. So yeah, and this is all a lot of speculative stuff at this point, right? Because the hardware is not fully baked out, and then software would have to be written, and now we're looking at monitoring the MER of every one of these sub carriers, and there'll be a lot more processing power too, right?
Yep, absolutely. Yeah. So
it's interesting.
Right. Anything else from the show last week you want to cover?
Yeah, I wanted to share. Let's see if I can share this. Let's see, share screen or screen share. I wanted to share a capture of one of the modems I took. Let's go. This was the full bandwidth capture of a modem. Can you see this okay?
Yes. Yes, looks good.
So this was 0 to 1 gig. So what I found interesting is, and this would work out well for a technician that goes to a house and the modem doesn't even register. Normally I thought about, this is all SNMP based, so the modem has to be online, it has to have layer 3 connectivity for me to even grab this information. But what if the modem doesn't come online? Well, you know, a lot of modems have this built-in sort of like a backdoor GUI website, 192.168. Can you see my mouse when I move it?
Yes.
Okay. Absolutely. So you see the 192.168.100.1. I plugged my PC into the Ethernet port of the modem. They usually will do DHCP on their own. And so my PC got a 192 address. And then I went to 192.168.100.1:8080. And it opened up the spectrum analysis view of that modem. So it already has a GUI in there. Now, the things I found out to make this work is I had to download onto my PC Google Chrome because I needed HTML5, I think it was. So my Internet Explorer, my Firefox, it didn't seem to work because it didn't have the right HTML. But when I downloaded the Chrome, I opened up Chrome, I put in that IP address, it opened up the spectrum analyzer, I hit run, I changed my span, I hit all my settings, but I'm essentially getting a downstream spectrum analysis view from the modem.
And the modem's not online with the CMTS. The modem's completely offline, which I think is really important for everyone that's listening. And if you're listening to this on audio, if you're downloading this on iTunes later on, what John is showing right now is a spectrum analysis display. So it looks like something you'd see off of an expensive spectrum analyzer, but it's coming from a cable modem, and the start frequency is 0 megahertz. And what's that go up to, John? A gig?
1 gigahertz.
1 gigahertz. So you're seeing everything that's coming into this subscriber's home, or in this case, maybe everything that's going out of the subscriber's home, from 0 to a gigahertz.
Yeah. So what's interesting is, if the modem's not coming online, you could use this to find out why it's not coming online. It could have been an RF problem. This spectrum analysis is independent of the modem's functionality, right? The modem's chipset.
Yeah, so this could be really a powerful troubleshooting tool for an installer going into a home that is having problems with the modem.
Yeah, and a lot of times I'll have handheld spectrum analyzers as well, but what if they don't, or, you know, there might be situations where this comes in handy. I mean, where we think it would be really handy is, you know, remote viewing from the head end when the modems are online.
If the modems are online, but when they're not online, that's the problem. Or if someone maybe can't afford to have a meter or a spectrum analyzer, this is quite nice to have, and quite nice to know that you have this capability built into the modem.
And what I'm really showing here is the big block centered up about 400 megahertz is my 32 single channel QAMs. So that's 192 megahertz worth of spectrum. The bigger one to the right is 96 megahertz wide of OFDM. So in theory, if I had a 3.1 modem, I could use the OFDM. I could be backwards compatible and just use the 32 QAMs, or I could combine both of them and bond traffic across both. And that's what the 3.1 spec is supposed to do.
So why are your OFDM carriers so much higher than your standard QAM carriers?
I knew you would say that. So I could give you I could give you the answer of, or excuse, that maybe this is a modem that is off the first tap where you have tilted output from an amplifier.
Yeah, that would make sense.
Correct. But it wasn't. So I could have gave you that, and I just did. But this is a case where it's all preliminary, and I couldn't figure out how to change the levels that were coming out on my OFDM channel.
Well, that also makes sense. And it's more believable.
Yeah, I'm not going to lie to you. And then some people might say, well, what about the noise floor coming out off the bottom of the OFDM? I mean, that might have been faulty connectors and cabling and whatnot. So at this point, I'm not really even worried about it. Like, people might look at that and say, if that's a real spectrum, if I put carriers right next to it, I'm going to have noise underneath my other carriers. Mm-hmm. Well, this is, let's look at it. 10, 20, 30, 40, that's 45 dB down. Yeah, it should be way down here, like 60 down, right?
Yeah, we went 60 dB rejection.
So that was 0 to 1 gig. Now, I talked to the manufacturer of this modem. It starts with a B. And even though it does read 0 to 1 gig, he told me this doesn't really have the upstream spectrum capability, which surprised me because I was able to zoom in from 0 to 85 megahertz, and every once in a while I saw upstream traffic pop up. So it's almost like, I don't know if my upstream traffic was bleeding across the diplex filter of the modem, hitting the spectrum analysis feature in the modem. You understand?
Yeah, I do.
Because really we'd want an upstream spectrum analysis on the low side of the internal diplex filter. And I think this doesn't have it, but actually I was seeing it kind of bleed across.
Right, and we did that demo a couple of Hangouts ago where we showed this vendor that begins with a B that has the they have it available. I think they have it shipping now in their modems where they do have the full return. So you get 0 to a gig, and you can see the upstream in the cable modem, which that is a very powerful troubleshooting capability. We're discussing in the ingenious working groups at Cable Labs on how you can correlate ingress noise that's leaking from a subscriber's home to the same noise that we see on the CMTS upstream. And we're trying to figure out ways that we can trigger on the noise in the head end and correlate to that noise that we're seeing at the subscriber home.
So I have some thoughts on that as well, and let me go through some more traces. So I also wanted to see what was the granularity of the spectrum analysis feature. So I was able to go as low as 6 megahertz of spectrum. Now on the upstream, I was able to go from 0 to 8 on this specific modem. It technically didn't support upstream, but I was still able to kind of zoom in 0 to 8. And I could see a little bit of noise. And the reason why I like to go down to 0 is what if there's AM radio noise coming in at the modem itself. AM is, what, 0.5 megahertz to 1.7 megahertz. So it'd be nice to be able to see the atomic clock at 2.5 megahertz. AM radio, there's a ham band at 3.5 megahertz. So there's some stuff below 5 megahertz that's always nice to see. Even though once it goes up to your first amplifier, the amplifier would usually block it out anyway. But if that AM radio is kind of everywhere, then maybe you can get an idea of how it might be getting into a node, closer to the node. So this is the 32 QAMs, zoomed into the 32 single channel QAMs. And then this was zooming in even closer so I can see the delineation between the QAMs, the 6 megahertz haystacks. And then this was the OFDM, 96 megahertz of OFDM. So
yeah, I think that's a really good illustration for people to see. I think people are afraid sometimes of OFDM, what's it going to look like? And from an RF perspective, it looks very similar to the QAM channels, the standard QAM channels that people are accustomed to looking at. So this is a really great illustration that OFDM in the RF world looks just like RF.
But here's the kicker, and maybe I was just being naive about it. When you think about the OFDM, we keep talking about 50 kilohertz subcarriers. And in the RF world, we always think, well, I should be able to zoom in and see 50 kilohertz subcarriers, almost like little carriers. But these 50 kilohertz subcarriers, that's where I'm doing the modulation, amplitude and phase modulation. They are actually slightly overlapped in a frequency type of display. So you're not going to be able to zoom in to individual, like 4,000 subcarriers. It's going to look like one big channel of noise, like one big QAM.
That's the orthogonal aspect of them.
Exactly. So when I explain it to people that, you're not going to be able to zoom in and see a 50 kilohertz carrier here, here, and here, and here, in the spectrum, the frequency domain, they're going to kind of overlap because you have the frequency and phase modulation. And it just looks like one big chunk of noise. Now, when we used the Rodian Swartz test equipment and zoomed in, it could actually pick out the pilot carriers, and the pilot carriers were spread throughout the whole channel, and you could see them about 3 to 6 dB higher than the average of the OFDM channel.
Right.
So it's kind of cool to be able to see the pilots, and I could see the region that was the PLC as well, the physical link control.
Sure.
This was zooming into where I thought LTE would fall, between 690 to 790, 800 megahertz. So I could see the band edge of my OFDM, and then I took my cell phone and turned on a YouTube and stuck it right next to a modem and an unterminated drop and unterminated cable, but tried to get it to pop in, and I couldn't seem to get it to pop in. So I was purposely trying to pick up LTE ingress, but I couldn't even see it on my Roden Schwartz either. So maybe this AT&T 4G that I had was actually at 1.7, or because I think
I think it's below 700 megahertz. If you said it's AT&T LTE,
yeah.
I think if you would have been a little lower in frequency, it might have been just below 700 megahertz.
That's why I wondered if it was, even if I was generating, was it hiding underneath my OFDM channel?
Yeah, I bet it was below your OFDM.
So that was kind of my full bandwidth capture type of slides in a nutshell. And it just gave me an idea of what I could see. So my thoughts on this, and maybe you're working with Cable Labs on this in the Ingenious group, is I would look at the CMTS noise. Then I would figure out a modem that has this capability on each leg of the node where I identified where the noise is coming from. But how do you determine that? Now, you could look at modem time offsets. Maybe the modem with the lowest time offset is the closest, but that one's a little touchy. Maybe you do it based on lat long, GPS, maps, billing, and you know where your customers are in the modems. So you identify the modem that has this capability that's closest to the node, so you can identify which leg it's coming in on. Now, if I have ingress coming from the end of line 5 amps deep, how is it going to get to that modem? It's going to have to overcome the isolation of the tap, go down this high value tap, feed the low side of the modem's diplex filter. Now, maybe it's still high enough that I could see it, but it's going to be dependent on this modem's dynamic range and capability of seeing noise, right? You agree?
Yeah, definitely. When you're looking at it coming from through a high value tap, that's going to be challenging. What we're more interested in is noise that's being generated within the home, and then it only has to go through a splitter. So if you assume that the modem is off of a splitter, in that case, it just has to go through.
So listen to what I'm saying. My point is, you don't want to haphazardly just grabbing modems all over the place. The best troubleshooting is divide and conquer. You find out which node it is, you find out which leg it is, then you go halfway, 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 and you narrow it down. If I go on to any which modem, that's a shotgun effect. You're just looking at every modem that has this capability and say, hey, let's see where it's coming in. You understand what I'm saying? There should be the smarts here to pick a modem that could identify which leg of the node, and then go halfway down. It's still there, so it must be further down the line. Halfway down, it's not there. Go back halfway. You understand what I'm saying? It's like the typical troubleshooting, right?
Yep. Divide and conquer.
That's it. Divide and conquer.
So, all right.
So more thoughts on this, right? This is the type of stuff that we can iron out, and I'm sure we can figure out how to automate a lot of this stuff, right?
Yeah, I think what we're waiting for is to get some population of those modems out there. Right now, we don't have much of a population to actually do any testing with.
I agree. So how about we get to the question stuff?
Yeah. Okay. So we have questions in our mailbox. Also, if you're listening, you can press the Q&A button and submit a question. Q&A button is in the upper right-hand corner of your of the screen. So first question we have came in from a listener last week on our hangout on security. And this is on a network with no DOCSIS 1X modems. Is there any downfall to enabling cable privacy, BPI plus policy, total enforcement? And it goes on to say, also on a 10K, it appears modems not supporting BPI plus are pushed to asterisk online or asterisk W online status. Guessing those have to have no network access. So they're asking about what that asterisk means. So I Dan Hagelin, who's on with us last night or last hangout, did respond to what that asterisk means. And he says that asterisk symbol next to the online state is there's a bug ID, DDTS, and that's CSCTJ59842. That and it displays the modems that fail BPI plus policy. The DDTS description says when modems fail the BPI plus policy, the modems come online PT, but are blocked from sending layer 3 traffic using a per device ACL, which is the access control list. So there's currently no way to see which modems are affected due to a new symbol that was added. Show modems that failed BPI plus policy.
So the new symbol that was added basically was the asterisk,
yes.
Right? So this DDTS, this bug ID, added and marked modems that were blocking layer 3, but they were still reporting online PT or PK?
They were online PT.
Yeah, okay.
But it's still being blocked.
Yeah, okay.
So, but the first part of the question, I think what wasn't addressed there was on a network with no DOCSIS 1X modems, so no 1.0 modems, no 1.1 modems, is there any downfall to enabling cable privacy, BPI plus policy total enforcement? And I don't know of any.
I don't either.
As long as you're using BPI plus, obviously.
Yeah. Which you should be.
which is what we recommended in our hangout last week. We highly, highly recommend that because it's one of the best ways to improve the security overall of your system. So so definitely use it. We don't know of any downfalls, and it's a best practice.
Yes.
So,
the only downfall I could think of. You don't get something for nothing. When I do capacity planning, I look at DOCSIS overhead. The DOCSIS header is always 6 bytes. On the upstream, we have an extended header that could be, I think the specs is 0 to 255 or something crazy. But when we do BPI plus, that extended header usually is 5 bytes. So there's an extra 5 bytes for BPI plus. If you're doing bonding, I believe it's another 6 bytes. And then on top of that, I just realized it took me I haven't really looked into IPv6 too much, but IPv6 changes the IP to a huge number, right? And any overhead that we had at layer 3 for IP headers has now increased to 20 extra bytes. And that affects potentially, and the reason why I brought it up was I had a customer wanted to do UGS, and I optimized my mod profiles, my AUGS mod profile burst, for a G711 20 millisecond packet cable call. As soon as we go IPv6, it adds 20 bytes to every one of those packets. So I'm like, it's not falling into my effect code word size very well. So now I affect T-byte overhead, and it's causing more overhead because I'm not really optimized the way I maybe could be. So I'm looking at my mod profile now to maybe manipulate it just for IPv6. But so the downfall for the BPI plus could be, well, you have 5 extra bytes for every single frame. But
yeah, so I mean, that's kind of I get your point. We're turning on BPI plus. We get a little bit of extra overhead, but we're trading that overhead for a lot more security and maybe keeping users offline that would be hacking into the system and using traffic that they're not paying for. Doing other things on the network that we don't want them to be doing. So I think it's worth giving up that extra overhead for it.
Yeah, and I just did 5 bytes divided by 1518 is 0.3%.
Yeah. Okay. So it's a drop in the bucket, man. Get over it. Okay, so next question. So we're using 8 upstream bonding channels today. Has it a lower data rate for each channel? So they're trying to calculate what they should expect as far as what data rate multiplier should they get for 8 upstream bonded channels. Do they calculate 8 times 30.72 megabits per second? Is that the data rate that they should expect?
So that when you say 30.72, that sounds like upstream. Are they taking my upstream 8 channel or downstream 8 channel? So
they're saying upstream bonding. So they're trying to figure out what's their data rate.
Okay, so normally 64 QAM, 6.4 megahertz channel width, usable rate is about 27 megabits per second. That's with 15, 18 byte Ethernet frames, all things being perfectly matched up, whatever. The 30.72 is raw rate. That's 256 QAM is 8 bits per symbol. 64 QAM is 6 bits per symbol times the symbol rate of 6.4 megahertz, which is only 5.12. So 5.12 times 6 is 30.72 megabits per second. That's raw. Well,
that's without the overhead that we were talking about, and BPI Plus and all that stuff.
Exactly. DOCSIS headers, and so 27 megabits per second. So if you take 8 times 27, that's, I think, 216.
Yep.
So you could get about an aggregate 216 megabits per second, 8-channel bonding of 64 QAM, 6.4 megahertz.
Makes sense.
Yeah. And then Absolutely. I would only offer maybe 100 meg service from that. You should never offer a service that could eat the entire pipe and starve everybody else.
Yeah, you're going to have some unhappy subscribers.
Yeah. Stat muxing doesn't work out too well. Statistical multiplexing doesn't work out well.
Yep. All right. Next question is in cable modem. This person wants to know the difference between registration complete and operational state online.
So he's doing probably like show cable modem command, and he can see all the modems that are registered, and that's different from all the modems that are actually online. So when modems come online, you have a NID-R1, a NID-R2, a NID-RC. That's the ranging part. It's done. Once you get done with that, then you're moving into actual layer 3 DHCP, TFTP, time of day server. Download the CM file, which is TFTP. That's the init-O, the options, and then the BPI Plus and all that. So I believe I answered this to you before that online basically means it's an online state PT, maybe online PT, W online, could be partial online, and it's fully registered. There could be a case where you have online PTD, which is it's done BPI Plus, it's online, I can ping it and all that, but the D stands for it's disabled, meaning that network capability is disabled.
Right, and maybe that would be done in the config file.
Yes.
It says network access 0, which means no access to network because maybe this person didn't pay their bill.
Yeah, well, you could have self-installs, right, where a customer goes, gets a modem, does a self-install, he goes to a walled garden to actually activate his modem.
Right.
Well, when you first plug it in, it might download a CM file that's either network disabled or I've seen people do this too, like 100 kilobit per second max throughput upstream and downstream, just so you could get to the walled garden and then upgrade to silver, gold, whatever, restart your modem. Yeah. Pick your package, restart the modem, it downloads the new CM file, and you're ready to go. So maybe that's what he was getting at with that question. He, she, I don't know who asked the question.
Okay, makes sense.
Yeah.
So next question, we have DOCSIS 3 CMTS, and we're using 4 upstream channels. We sometimes see that one of the DOCSIS haystacks, is much higher, is at a much higher level than the other 3. So they have 4 upstreams. One of the upstreams is a higher level in RF. Can you tell me what would cause this? Only on some nodes are we seeing this.
So this is interesting. One, if they're different channel widths, they will be 3 dB different if they're half the channel width, relative half the channel width, meaning a 3.2 megahertz wide channel will be 3 dB higher than a 6.4 megahertz wide channel because we keep same average power. But it sounds like they're all the same channel width. That's what I'm inferring from what he's implying here.
So that's what we have to assume that, especially if they're doing.
Yeah. Let's assume they're all the same channel width, and he's saying much higher, not 3 dB, right? So he's saying much higher.
Yes.
So then it comes down to, you can change the upstream power level on an upstream channel basis in the CMTS. So let's go back and make sure that's set at the default of 0 across the board. Mm-hmm. If it's not, well, there's your problem, right? So a lot of times the RF tech doesn't know what the IP tech is doing. He might have went into the CMTS and changed upstream 3 to be +5, and upstream 0 is 0.
Yeah.
So it's actually telling the modem to transmit hotter at the other frequency, the other channel. Let's assume that that's not the case. The next thing I could think of would be, where's your test point pickoff? You know, what if you have upstream 3 at 38 megahertz center frequency, and because it's in the roll-off, sort of the roll-off of diplex filter, or maybe it's just roll-off in the cable plant or something weird.
You're thinking 3 equalization.
Modems would have to transmit hotter to overcome that extra attenuation. And depending on where your test point pickoff is, maybe you're seeing that. At the CMTS, it would be flat, because the CMTS tells the modems to transmit high or low.
Right.
Hit the CMTS flat. But depending on where your test point pickoff is, that might look distorted. Like my path track could be picking off right at the optical receiver and head end, but what if I had roll off between that point and the CMTS? The path track doesn't see that roll off, but the CMTS does. So the CMTS tells the modems to transmit different levels so that I can hit the CMTS at 0. Well, at the path track, it's not seeing that adjustment. You understand?
Oh, no, absolutely. And it's difficult sometimes to get a test point right at the input of the CMTS.
Agreed.
So
there's like 3 scenarios there I could think of.
Yeah, it's difficult. All right, so I have an upstream. This is another question. I have an upstream channel. It's set at 3.2 megahertz bandwidth. Its modulation is QAM 32. I can only seem to get 4 megabits per second on the upload for this modem. The modem shows channel type of mixed TDMA and ATDMA, symbol rate of 2.56 megasymbols per second, and 32 QAM modulation. According to everything I've read, I should get 12 megabits per second on the upload. Your updated version of the modulation profiles you wrote has these 2 lines, and there's a couple lines. These come from my blog. It's based on our recommended modulation profile that you and I did. And I think there was a typo in there that's based on the, is it 152 no diff 152 or 152 no diff 64? And I think that was a typo. But we talked about, mixed mode would be a mod profile 124 variant of 1XX.
Yeah, a mixed mode allows 1X modems to use some of the bursts, and 2.0 modems and 3.0 modems to use the advanced long, advanced short, advanced UGS bursts. So I assume 1X can't do 32 QAM, so his mixed mode was probably doing 16 QAM maybe for the data burst, short and long data burst for 1X modems, and 32 QAM for the 2.0 modems. Now, I don't like odd constellations. I don't like 32 QAM. The constellation is not a clean type of constellation. It's like taking a 16 QAM constellation and then shifting another 16 QAM up like this. So you have outer symbol landings is almost the same as if it were 64 QAM on those 2 outer points. Maybe not on these points, but on these points. So you don't get the 3 dB robustness that theory would usually equate to. So I'm like, just go to 64 QAM, keep it simple. It's a nice even constellation. And if you don't like that, you could drop to 16 QAM. There's a big enough jump there to make a difference in robustness.
So I've actually seen issues with some modem vendors using 32 QAM when I've gone into systems that were set up with 32 QAM, and by either going to 16 QAM or 64 QAM, I've seen a dramatic improvement with those modems across the board. And I don't know if you've seen this or not, depending on what modems, but I completely agree with you when you say you don't recommend 32 QAM, and I think it's just not widely used and widely tested across the board. So because people are not using it a lot, it seems to be one of those modulations that it's I don't know if it's just not.
It's flaky.
It's flaky. It is absolutely flaky. And so that's the one. One of the things I'll go with clients and say, you're using 32 QAM. I'd really recommend, and you're having issues, you're having modems go offline, you're having data transmission issues. I'd really recommend we either go to 16 QAM if your plant can't support 64, or we go to 64 QAM, or we do a dynamic modulation profile that is both 64 and 16 QAM, depending on how the plant is working.
Yeah, I'm like, don't we have enough variables to deal with that we don't need to add more? I mean,
absolutely.
Keep it simple, stupid. The KISS principle. Let's keep it
Yep.
simple. I like the fact that I have these nerd knobs and I have these little things I can tweak, but we used to call that for the expert users or the people that really knew what was going on. Let's just keep things simple, and then if we really want to tweak things and we understand it better, then we can do that. But 32 QAM I don't recommend. Now, he is correct. I assume it's a he. 32 QAM is 2 to the 5th power, so that's 5 bits per symbol, times a 2.56 megasymbol per second symbol rate would give me about 12 point whatever, maybe 13, if you do the math, megabits per second raw. But is it raw?
Yeah, 12.8 megabits per second raw, but you're probably going to get about 11 megabits per second usable.
Exactly. So you get about 11 megabits per second usable. Now, the question or the concern was, I can only get 4 megabits per second on the upstream. Well, now you're talking about per modem upstream speed. That's totally different from aggregate speed. I suspect that if he hooked up 8 modems all doing 2 megabits per second, he would reach the full usable rate and 100% utilization, meaning 11 megabits per second. Yeah. But he's trying to do single modem speed, which is request, grant, request, grant. There's a lot of little tweaks we need to do to get really above 3 megabits per second, usually. So with the DOCSIS 3.0 modem, because it does continuous concatenation and fragmentation, it might get better per modem speed than, say, a 2.0 modem, assuming it's in MTC mode, which is, it might do single channel, but it's single channel bonding, if you will. It's not really bonding any channels, but it's doing single channel, and it will get better speed than a 2.0 modem in a single cable modem upstream speed test.
Yeah, that was an interesting trick that you taught me, that even though you're not doing upstream channel bonding with 3.0 modems, turning on MTC mode actually improves your upstream throughput or your overall throughput speed.
Yeah, the modem could pick one of our default single channel bonding groups. That, to me, it sounds like an oxymoron. Single channel bonding group.
It doesn't make any sense at all, but it actually works.
So what it does is it puts the modem in MTC mode, which allows the 3.0 modem to do CCF. CCF is this continuous concatenation and fragmentation, which allows me to do a request grant much faster. So single channel upstream speed tests are much better with the 3.0 modem in 3.0 upstream mode.
Yeah. Another thing for listeners to realize, and this confused me for a while when I first started working with 3.0 modems, is I would do like a show cable modem for a BOS, and I would see the concatenation and fragmentation was disabled in DOCSIS 3.0 modems. So I'd quickly go back to the config file and start trying to figure out why concatenation and fragmentation was not enabled in the modems. And I think it was you that probably told me that that was because of the advanced way that DOCSIS 3.0 modems use the continuous CCF.
Yeah, CCF.
Yeah.
So when you look at the modems for BOS, it'll say, like you said, concatenation off or no, and fragmentation no. It's like, whoa, is this a 1.0 modem? Did it download a 1.0 CM file? And then you find out, no, it's in 3.0 mode and it's doing CCF, so it doesn't need to have that functionality. Now, so in my CM file, people ask me, what should I put in the upstream max concat burst? Well, in theory, if a 3.0 modem is not doing this concatenation, any changes there won't have an effect on the modem's operation on the upstream. But I tell people, set it to the same you would do for a 2.0 modem, like 8,000 bytes, because what if the 3.0 modem for some reason registers in 2.0 mode? If you don't have a good setting in the max concat burst field, that 3.0 modem could get worse upstream speed than the 2.0 modem.
Right. And you always have to expect, I mean, most people are giving the same config files a lot of times to 3.0 modems that they are to 2.0 modems. So you do want that max burst setting for your 2.0 modems, or they're going to get really poor upstream throughputs.
Yep.
So
we're running low on time, aren't we?
Yeah, we are, John. We're out of questions, so it's another hangout that we have got under our belts. So.
All right, cool.
All right, thanks for your time. Have a good day. We'll talk to you later.
All right, see you guys.
See y'all.